We were looking at a massive new collaborative survey paper today titled Graph Engineering in the Era of LLM Agents, From Individual Intelligence to System Intelligence. This is a joint effort from institutions like Jilin University, Shanghai AI Lab, HK PolyU. And the core insight here is basically a wake-up call for the entire field. We have officially hit a structural wall with single LLM agent.
Yeah, a massive wall.
Right, because to solve complex, long-horizon, real-world tasks, things like autonomous software engineering or end-to-end scientific discovery, we can't just make individual models smarter or give them larger context windows. The paper introduces this concept of graph engineering, which is using dynamic, evolving graph structures to organize tasks, coordinate specialized heterogeneous multi-agent teams, and explicitly manage runtime execution states.
Exactly.
So, okay, let's unpack this. We are basically moving from prompting a single brain to architecting a digital corporation. Welcome to this episode of AI Paper Slop, the YouTube series where we summarize the most important AI and tech papers you need to know about.
Yeah, and the ML community has been running on this assumption for a while now that if we just scale the reasoning capabilities of a single model, like if we just make it big enough, it will eventually be able to do everything.
Right, just throw more compute at it.
Exactly, just throw more parameters at it. But this paper maps out a taxonomy of AI evolution that basically proves why current single-agent architectures are fundamentally failing in production environments.
Oh, wow.
We have essentially hit a sequential processing ceiling.
Okay, so before we get into how graph structures actually shatter that ceiling, we need to trace that taxonomy to see exactly where the breakdown happens, because I think people need to understand the history here.
Yeah, that's crucial.
The paper starts the timeline at what they call model intelligence. And this is the foundational layer we're all familiar with, right? It's established through parameter-level training, so pre-training and post-training on models like Llama 3 or DeepSeek Math.
Right, the base models.
Exactly. And we elicit that intelligence using prompt and context engineering, things like chain of thought or RAG.
Right. And the thing with model intelligence is that it's entirely bounded by a single inference process.
Okay.
You give it a static input, and it generates a static output. That's it. So to get to where we are right now in the industry, which the authors define as individual intelligence, we had to build all this scaffolding around the model.
Scaffolding, right?
Yeah. And the paper categorizes the scaffolding into two things. Harness engineering and loop engineering.
Harness and loop? Oh.
Yeah. So harness engineering connects the model to external tools. APIs, code interpreters, persistent memory stores. We're talking about frameworks like MemGPT or SWE-agent.
Oh, yeah. I've used SWE-agent.
Right. And then loop engineering wraps all of that in persistent cycles. So it's planning, acting, observing, and verifying, just looping over and over.
So I like to think of model intelligence as this brilliant but completely isolated graduate student locked in an empty room.
That is a great way to look at it.
Right. Like they have an encyclopedic knowledge of computer science, but they can't actually compile code or see a repository.
Right. They just have the theory in their head.
Exactly. So individual intelligence is when we finally give that grad student a laptop, shell access, and a loop, which is basically a force schedule that keeps them reading tickets, writing code, and checking test outputs over and over again.
Yeah, you've put them to work.
Right. But let's ground this in a real scenario for the engineers listening to this deep dive into the source material. Imagine we want an agent to migrate a massive, like a 1,000,000-line monolithic backend from Python 2 to Python 3.
Oh, gosh. A nightmare project.
An absolute nightmare.
Yeah.
Stuff of legacy code terrors. But if we can give an agent an infinite loop and a full suite of shell and editing tools, why can't a SWE agent just loop infinitely through that repository until the migration is finished? Like, what's stopping it?
Okay, so this is where it all breaks down. Because a massive Python migration is not just a long task, it's a structurally complex task. It has interdependent branching states. So when you force a single agent loop to tackle that, you create this catastrophic sequential bottleneck.
A sequential bottleneck, meaning it can only do one thing at a time.
Exactly. The agent has to read a dependency file, then it has to analyze a class structure, attempt a syntax rewrite, run a unit test, read the traceback, and modify the database schema to match the new string formats.
Right. All in order.
Right. And every single one of those actions, and all of the context associated with them, it all competes for the exact same contextual capacity within the model's memory buffer.
Wait, here's where it gets really interesting, though. Because as ML engineers, we know models like Gemini 1.5 Pro or Kimi K2 have these massive context windows now, right?
Right, millions of tokens.
Yeah, up to millions of tokens. So you could literally fit the entire Python 2 code base, the target Python 3 documentation, and all the test logs into a single prompt.
You could, yes.
So if memory size is the issue, why can't the agent just hold the entire project state in that massive context and just keep cycling? I mean,
Yeah.
How doesn't that work?
Because a million token context window is just a gigantic, unstructured memory buffer.
Unstructured.
Yes. It is not a task scheduler. It's not a structural organization mechanism. The authors highlight that when you just shove the states of concurrent, heterogeneous tasks into a single shared context, you inevitably trigger severe loss in the middle syndrome.
Oh, right, where it just forgets the stuff in the middle of the prompt.
Exactly. The attention mechanisms just degrade, but more importantly, you destroy reasoning isolation.
Reasoning isolation. What do you mean by that?
So think about it. If a single agent is trying to refactor a database driver while simultaneously trying to fix a broken API endpoint in another module, the state representations and the context window bleed into one another.
Oh, wow.
Yeah. You start seeing the agent hallucinating variable names from the database driver into the API endpoint code simply because they are sitting next to each other in the prompt.
Oh, man, that's terrible.
It is. A single sequential loop cannot isolate concurrent work or synchronize shared results without completely fracturing the agent's reasoning trajectory.
That makes perfect sense at an architectural level. It's exactly like trying to run a modern multi-threaded operating system on a single core processor with absolutely no task scheduler to manage the threads.
Exactly.
You just get a bottlenecked, deadlocked mess.
Complete deadlock.
So scaling up a single agent's context or loop is basically a dead end for complex engineering tasks.
It's a total dead end.
Which brings us to the paradigm shift. The architecture has to move to distributed systems.
Yes.
And this is what the paper defines as system intelligence.
Right.
Distributing the cognitive load across specialized agents that are organized at a system-wide level.
Right. But the crucial distinction the authors make here is that a multi-agent system does not automatically possess system intelligence.
Wait, really? Just having multiple agents isn't enough?
No, not at all. You can spin up 20 Llama 3 instances in a framework, but if they lack a strict structural coordination mechanism, you don't have system intelligence. You just have expensive chaos.
Expensive chaos, yeah. That's a good way to put it.
Right. True system intelligence requires a completely new underlying substrate, which is graph engineering. And the paper structures this around 3 pillars:
Okay, let's hear them.
task organization, agent coordination, and runtime state management.
Okay, so if cramming everything into one context window causes this, memory bleed that you were talking about, how do you actually enforce those boundaries? Like, you have to physically separate the workload, right?
Precisely.
Which brings us to pillar 1, task organization, or figuring out exactly what needs to be done.
Right.
So instead of feeding a monolithic prompt like migrate this code base to Python 3 into a single agent, the system decomposes that global objective into explicit subtasks and dependency relations.
Yes, breaking it all down.
And it represents this as nodes and edges in a directed acyclic graph, or a DAG.
Exactly, a DAG. By utilizing a DAG, the system mathematically codifies the execution order.
Okay.
So it knows that refactoring isolated utility files, let's say 10 different string parsing modules, can be executed as parallel nodes. They don't depend on each other.
Right, you can just spin up 10 agents to do those at the same time.
Exactly. But it also knows that the core database migration node has a hard edge dependency on the completion of the schema update node.
Oh, so it can't even start the database migration until the schema is done.
Right. The system is no longer just guessing what to do next based on the last few tokens generated in a loop. It is traversing a deterministic graph structure that guarantees dependencies are resolved before dependent tasks begin.
Okay, so once the system knows what the tasks are, we get to pillar 2, which is agent coordination. This handles who does the work and how they talk to each other.
Right.
So once the task graph is mapped, the system maps specific agent capabilities to those task nodes. But from what I read, it goes way further than just role assignment, right?
Much further.
It explicitly defines the communication topology. The graph dictates the exact routing of information.
And this is exactly where we solve the context bleed problem.
How so?
Well, in standard multi-agent setups, they often rely on a shared blackboard or a broadcast communication style.
Oh, like where everyone sees everything.
Exactly. Every agent sees every message from every other agent. But with graph-engineered agent coordination, you are enforcing strict reasoning boundaries via bipartite graphs or customized topologies.
Okay, give me an example.
So if coder agent A is assigned to refactor a specific API endpoint, it has a directed edge connecting it to the QA reviewer agent.
Okay.
But it has absolutely no edge connecting it to the database specialist agent working on the schema. Therefore, no information flows between them, none.
I always compare those older broadcast multi-agent setups to a chaotic Discord server.
Oh, that's exactly what it is.
Yeah. You have 5 agents in a chat room. The database agent is printing out SQL schemas. The front-end agent is talking about React components. And eventually, the back-end agent starts hallucinating SQL syntax into a Python route just because it's reading the database agent's chat history.
Yeah. That just bleeds in.
It's a mess. But this graph-engineered topology is like a highly optimized CI/CD pipeline mixed with a strict corporate org chart. Information only flows where the edges dictate.
And by restricting the flow of context like that, you drastically increase the precision of the agents.
Because they're only seeing what they need to see.
Exactly. When the coder agent finishes its task, the edge routes only the final get diff and the explicit acceptance criteria to the QA reviewer agent.
Right.
The QA agent's context window is pristine. It isn't cluttered with the 5 previous failed attempts the coder agent made.
Or like the chain of thought scratchpad it used to figure out the code.
Exactly. It only sees exactly what it needs to evaluate the code. This architectural isolation is what makes the system efficient and dramatically reduces hallucinations at scale.
Okay, so we've mapped out the DAGU for the task, we've assigned specialized agents to the nodes, and we've tightly restricted their communication channels. In theory, our Python migration is humming along perfectly.
In theory.
Right, in theory. But as any ML engineer who has ever deployed anything knows, the real world is incredibly noisy.
Very noisy.
Things break in production all the time. If we were running a massive asynchronous graph of agentic tasks and something goes wrong at, I don't know, step 500, we can't just throw an exception and restart the entire system from scratch.
No, you'd waste hours and thousands of API calls.
Exactly. Which brings us to pillar 3, runtime state management. I think this might be the most important part of the paper.
It is. Runtime state management is what separates a fragile script from a resilient enterprise-grade system.
Right.
In these long horizon autonomous tasks, the visible error is almost always structurally detached from the root cause.
Meaning the place it breaks isn't where the bug was actually written.
Right. A unit test might fail on step 500 during a system-wide compilation check, but the actual bug was introduced back at step 420.
Oh man, the worst kind of bug.
The absolute worst. If you don't have a way to manage state, the system is permanently stuck. To solve this, the paper details 3 mechanisms, beginning with state recording.
Okay, state recording.
The system continuously logs the execution of the graph. It tracks the planned states against the actual executed states and builds a comprehensive versioned provenance graph of every single transition.
Okay, so it's not just logging text output. It's physically recording the node states, the inputs and the outputs at every edge traversal.
Yes.
It's maintaining a highly structured git commit history for the system's entire thought process and execution paths.
Exactly. And because every action is logged as a node in that provenance graph, the system can execute the second mechanism, which is fault localization.
What localization?
Right. It doesn't just pass the error to a generic debugging agent and say, fix this. Instead, it performs a backward topological search through the DAG.
Backward topological search, so it goes in reverse.
Yes. If a compilation fails, it takes that failure state and traces back through the specific dependency edges. It programmatically compares the output state of each historical node against its initial validation criteria.
Okay.
This effectively isolates the exact edge where the logic diverged from the expected path. It might pinpoint that a variable renaming task handled by a specific agent 3 hours ago is the root cause of the compilation failure right now.
Wait, hold on. I have a major engineering question here.
Sure.
If the backward topological search localizes a fault to an internal memory state, like a badly written Python script sitting in a local directory, a rollback is easy. It just reverts the file and spins up a new path on the DAG, right?
Yes, that's trivial.
But what if that agent already took an external action? What if, as part of that faulty execution path, an agent pushed a bad commit to a live external repository or sent a deployment notification email to a Slack channel.
Oh.
You can't just delete an agent's memory sending a Slack message and pretend it didn't happen in the real world.
No, you cannot. That is the exact challenge of distributed agentic systems, and it brings us to the third mechanism, failure recovery.
Okay.
The authors address this by mapping the graph execution to what ML engineers will recognize as Saga distributed transaction patterns.
Oh, Saga patterns, like in microservices.
Exactly like in microservices. The system's graph explicitly distinguishes between internal computational states and external environmental effects. When the backward search identifies the fault, the system calculates a recovery boundary.
So it figures out the blast radius of the bug.
Precisely. For internal states within that blast radius, it executes standard rollbacks. It reverts the internal memory and files to the last valid node before the fault, preserving all the valid parallel work on other branches of the DAG that weren't affected.
That's super smart, so it doesn't lose the good work.
Exactly. But for external effects that cross the boundary into the real world, a simple memory rollback is physically impossible.
Right.
The graph flags those specific edges as requiring compensating transactions.
A compensating transaction.
Right. This means the system must dynamically generate and insert new nodes into the DAG to actively undo the real-world action.
Okay, give me an example of that.
So if it pushed a bad commit, it generates a task node to execute a git revert and push the reversion. If it sent a Slack message, it generates a task node to send a follow-up correction message. Only after those compensating nodes successfully execute does the system resume the primary workflow from the rollback point.
That is incredible. It is genuinely treating the multi-agent system like a distributed database handling distributed microservices.
It really is.
You have strict commits, bounded rollbacks, and programmatic compensation logic for external side effects. This is what makes the system structurally robust enough to actually deploy in a production environment.
Exactly. It's safe.
Now, we've built this highly resilient system. The final frontier the paper explores is what happens when we run the system hundreds of times. Like, how does the architecture itself adapt? And they introduce the concept of system evolution.
Yeah, and it is crucial to distinguish between simple runtime adaptation and true system evolution.
Okay, what's the difference?
Well, runtime adaptation is everything we just discussed with failure recovery. Dynamically routing around a bug, inserting a compensating transaction, or temporarily altering a prompt to complete the current running task.
Right, just fixing things on the fly.
Exactly. System evolution, however, is the process of using the accumulated execution evidence from completed tasks to permanently alter the underlying graph structure for future tasks.
Okay, I want to make sure we nail the mechanics of this for the engineers listening. How does it actually evolve? Are we talking about the system running a reinforcement learning algorithm over its own execution graph to find optimization pathways?
That is exactly the mechanism. The system treats its own organizational topology as a trainable parameter space.
Wow.
It applies RL algorithms or evolutionary heuristics over the historical provenance graphs. Let's return to our Python migration example.
Okay, yeah.
Suppose the initial degreg specifies that every piece of code written by the coder agent must pass through a strict manager agent for formatting approval before going to the QA reviewer agent.
Like a human org chart.
Right. But over 20 migration tasks, the system analyzes the execution graphs and notices that the manager agent node adds 40 seconds of latency to every cycle, but results in 0 functional changes to the code.
Because the coder agent is already using an auto formatter or something?
Exactly.
So the system mathematically proves that the manager agent node is basically dead weight.
Right. The evolutionary algorithm identifies that bypassing the manager agent entirely and linking the coder directly to the QA reviewer yields a 15% efficiency boost without impacting the validation success rate.
Oh, it's wild.
And it then modifies the topology weights permanently. For the next 100 migration tasks, that manager node is excised from that specific workflow, and the bipartite graph is rewired. The system is fundamentally altering its own org chart based on empirical performance metrics.
But how do we even evaluate something like that? The paper points out that our current AI benchmarks are totally inadequate for this paradigm.
They're completely useless for this.
Right now, benchmarks just look at the final output. Did the agent pass the coding test? Did it solve the math problem? If we have systems that are dynamically rewriting their own distributed architectures, evaluating just the final output is like grading a massive corporate merger based solely on one-day stock price.
Exactly. And the authors argue forcefully for a new generation of benchmarks. We have to move beyond outcome-based metrics and measure what they call structural fidelity and operational correctness.
So measuring the process, not just the product.
Right. We need programmatic ways to evaluate the validity of the DAG itself. Did the backward topological search accurately isolate the correct edge? Were the compensating transactions actually proportional to the external side effects?
Yeah, like did it send a reasonable correction message on Slack, or did it just spam the channel?
Exactly. And when the system evolved its topology to remove that manager node, was that evolutionary step mathematically sound and traceable, or did it just get lucky on a narrow data set? We need tools to verify the integrity of the graph operations, not just the final text the agents spit out.
So what does this all mean for the researchers and engineers tuning in right now? I think the absolute clearest takeaway from this deep dive into the source material is that the era of relying solely on clever, massive prompts to solve hard problems is coming to an end.
It really is.
If you are building AI agents today, your career trajectory is shifting from cognitive engineering to organizational engineering. You aren't just tuning model weights or building better RAG pipelines. You are architecting distributed systems.
Yeah.
You have to understand directed acyclic graphs, compensating transactions, and topology optimization.
It represents a profound maturation of the AI field. We are transitioning from maximizing the cognitive capabilities of isolated nodes to optimizing the structural capabilities of the system as a whole. The true intelligence of future AI platforms will increasingly reside in the edges of the graph, how efficiently and dynamically the agents are connected, rather than just the raw processing power of the nodes themselves.
Which leaves me with a final, slightly provocative thought to mull over.
Okay, let's hear it.
If we are giving these AI systems the algorithmic ability to continuously evolve their own graph topologies, and they are using reinforcement learning to permanently rewrite their team structures and communication pathways based on pure execution efficiency, will we eventually see them invent entirely alien management hierarchies?
Oh, that's a wild thought.
Right. Imagine looking at the provenance graph of a highly evolved multi-agent system a year from now and seeing workflows, communication bottlenecks, and organizational structures that human engineers completely lack the intuition to comprehend, simply because they are mathematically optimized in high-dimensional space rather than based on, human management theory.
We might not even be able to understand our own system's workflows.
It's an incredible engineering frontier. Just some food for thought.
Yeah.
Thanks for joining us on this deep dive into AI paper slop, and we'll catch you on the next one.